So hello everyone, welcome back. So in today's video, we'll try this unofficial sample paper from IIT Kanpur. And I'm just trying it out for the first time. So if I make any mistakes, I'll later deal it in the comments. Okay. So the first problem is from dimensions. So we have frequency of the oscillation on the left side, and we have mass, radius, and they're saying a third variable x, where it is either the universal constant g or the surface tension s. Okay, so the dimensions of the universal gravitational constant is, so if it will be fr squared divided by m1 m2, right? So there'll be a mass to the power -1, and there'll be a meter cubed, so L cubed, and the time is just from the acceleration, so it will be t to the -2. Okay, and the dimension of the surface tension will be force over length, which would be, so it'll be mass to the power 1, and the length would be meters by meter, so it'll be length to the power 0, and time is once again just from the acceleration term, which is t to the -2. So the dimension of time is identical for both, so we can say t to the power -2 gamma is the overall dimension of time. Now for frequency, it has the dimension of time inverse, time to the power -1, so gamma has to be half. Okay, so these two options are wrong. And now if you compare beta, now beta is the dimension of the length. As gamma is half, if x has the dimension of the gravitational constant, the length dimension will be L to the power 3/2. X contributes a length dimensional factor of L to the power 3/2. And so obviously beta would be -3/2. Right, and the dimension of mass would be m to the power -half, so alpha should be +half. Okay, so the B option looks correct, and in C option, now if x has the dimension of the surface tension, okay, so the dimension does not depend on the length, which means beta is 0 in this case. Okay, and the mass dimension, we have a power raised to half, so alpha needs to be -half, so C option would be wrong. Okay, so yeah, also this is like the single correct anyway. So yeah, the answer to this will be B. Now to this question, we have unpolarized monochromatic beam of light that is incident on a planar interface of two media of refractive index N1 and N2. At an angle of incidence I, it is found that the reflected beam is completely polarized. Now, if the reflected beam of an unpolarized light is completely polarized, it means it is incident at the Brewster's angle. So basically tan of I is the refractive index of the second media, so N2 over N1. Okay, so that would be D option. Now for A option, they're saying N1 is greater than N2 and I is greater than 45. So this would be wrong, because if N1 is greater than N2, then tan of I is less than 1 or I is less than 45. And in the second case, they're saying this is wrong anyway, because I is tan inverse of N2 by N1. So the answer to this would be just D. Okay. All right. So in this problem, we have a mole of ideal monatomic gas undergoing a thermodynamic process, where processes 2 to 3 and 4 to 1 are isothermal, and they carried at temperatures 1 plus beta T0 and T0. So we have to say which of the statements are false. Okay, so the cycle direction is from 1 to 2, 2 to 3, 3 to 4, and from 4 to 1 once again. The total work output is just the area under this curve. Okay, so the heat input from step 1 to 2, the process 1 to 2 would be Cp multiplied by T2 minus T1, which is just Cp multiplied by, now T2 is 1 plus beta T0 and T1 is T0. So the difference would be just beta T0. Okay, and the work done by the gas is just the pressure P0 multiplied by the change in volume, V2 minus V1. So if we apply the ideal gas relation for the process 1 to 2, we can say P delta V equals NR delta T. So N is 1. So delta V, we can just write it as R delta T over P. So this would be R times delta T, which is T0, divided by P0. So this is just going to be R T0. Okay. Now the heat transfer in the process 1 to 3 is just going to be equal to the work done in step 1 to 3. And they are both equal to R times the temperature, which is 1 plus beta T0 times ln of V3 by V2. Okay. So now if you observe the process 2 to 3, and if you apply ideal gas relation, so here temperature is constant, meaning the product PV is constant. So if this is V2, then we can say P0 V2 equals P0 by alpha multiplied by V3. So from here, V3 by V2 is just going to be alpha. Okay. So this over here is just R T0 1 plus beta multiplied by ln of alpha. So now the work done by the gas in the process 3 to 4 is once again P delta V. It's isobaric. So we can say it is equal to negative P0 by alpha times delta V. Okay, and once again delta V, we can write it as R delta T divided by the pressure. Even this is effectively R T0. And now we have the work done from 4 to 1. This is once again an isothermal process. So this will be negative R T0 ln of V4 by V1. Okay, so now in this branch, as the temperature is constant, we can say PV is constant. P0 V1 equals P0 by alpha times V4. From here, V4 by V1 is once again equal to alpha. Okay, so now if you add all the work terms, you'll get the net work output by the gas. So the RT naughts cancel, the negative RT naught ln alpha cancels, and the answer we get is RT naught beta ln of alpha. So this is the net work output of the cycle. Now the heat that is given as input to the gas is Q12 plus Q23, okay, because in the other two processes we have heat leaving the gas. So if we add Q12 and Q13, we get RT0 1 plus beta ln of alpha plus beta Cp T0. So now the ratio of these two is what efficiency is of the engine. It's the ratio of the work output that we get for providing a given heat input. So in the first option, they're saying if alpha is 2 and beta is 1 by 4, then the efficiency is. Okay, so the efficiency in that case would be, so the work would be RT0 beta by 4 times ln 2. And the second term is going to be RT0. 1 plus 1 by 4 is 5 by 4. And then we have ln of 2. Now CP4, a monatomic gas, is 5R by 2. Okay, so this becomes 5 by 8 RT0. So of course there won't be a beta here, it will be 1 by 4. So now you can cancel out the RT naughts. Now they wanted you to use the value of ln2 as 0.7, and in the denominator we have a 5 ln2 which is 3.5, and then we have a 5 by 2 which is 2.5. So this is 0.7 divided by 6. Okay, so now this is going to be 0.11666666 and so on. So if rounded off, this comes to be approximately 0.12. So and now the second question, they wanted the ratio of the transfer in the process 2-3 to the process 1-2. So that is basically this thing divided by this thing, right? So this ratio is going to be 1 plus beta ln2 divided by, so 1 plus beta is going to be 5 by 4. ln2 is 0.7 divided by Cp is going to be 5 by 2 multiplied by beta is 1 by 4. So we can cancel out a 5 by 4 and we get the answer as 1.4. So even this is correct. Okay. Now the work done in the thermodynamic cycle 1, 2, 3, 4, 1 is, so that we just figured out earlier, it is equal to RT naught beta ln of alpha. So this would be wrong. Okay. Now the D option, beta much less than ln of alpha. The efficiency of the cycle approaches that of a Carnot engine working between the same maxima and minimum temperature. Alright, so let's once again write down eta. And this time we'll make the numerator 1. So basically we'll divide the numerator and denominator with W. So this becomes 1 plus beta divided by beta. And the next term becomes beta Cp divided by R ln alpha. Okay, so now if beta is to be considered significantly smaller than ln alpha, then we'll basically neglect this term. Okay, and then the efficiency approaches beta divided by 1 plus beta, right? Okay, so if you multiply and divide with the T naught, both in the numerator and denominator, this is just 1 minus T naught divided by 1 plus beta T naught. So this is basically the efficiency of a Carnot engine working between these two working between the minimum temperature of T naught and a maximum temperature of 1 plus beta T naught. So option D will also be correct. Okay, so the answer will be C. I mean, of course, if you're writing this in an exam point of view, you already have the answer. I'm just going through each options one by one. So now in this problem, we have a 1D box of size L, which contains 4 electrons whose mass is ME. Okay, so we are defining E naught as the ground state energy and alpha as this particular constant, and H is given to be the Planck's constant. So we have to assume that the electrons are non-interacting and they obey the Pauli exclusion principle and are described by standing de Broglie waves confined within the box. Then we have to comment on these 4 options. Okay, so this problem is from a topic called as electron traps. Okay, you can find it in books like Halliday-Resnick or Halliday-Resnick and Crane. I mean, it's not formally in your syllabus, but so I'll just try to explain this. But if you're new to it, you would have to study it to understand it, right? So basically, you have a one-dimensional box. So we only care about one dimension, and we have to trap 4 electrons within this particular box. So so what that means is the probability of finding an electron to the right of this box and to the left of this box should diminish to 0. Now, when you solve the Schrodinger's equation for the matter wave in this particular situation and use the boundary conditions that close to the boundary, the probability of finding an electron should go to 0, then the solution we obtain for the wave function is similar to that of a standing wave. So the solution for the matter wave, similar to the standing wave, it will be something like an amplitude multiplied by sine kx times sine of omega t, similar to what we see in a standing wave. So here in this one-dimensional trap, the boundary conditions is that at the end points should be a node for the matter wave, because the probability of finding an electron at the ends is going to be 0, and the probability of finding an electron in a closed volume close to a point is proportional to psi squared. Okay, so I mean that's the story of the game. So basically, as we don't want to find an electron towards left of this point or towards the right of this point, the probability diminishes to 0 towards the ends, and the value of psi becomes close to 0. So meaning these act like the nodes for our standing matter wave. Okay, now the wavelength of the matter wave can be different, is basically the de Broglie wavelength, so that's going to be h by p. And for the electron we can write the momentum as square root of 2m kinetic energy, right? So now the thing is, as the electrons are non-interacting, here the kinetic energy is itself the total energy of an electron as well. Okay, so now the thing is, using the boundary conditions we learn in standing waves, we can write L as an integral multiple of lambda over 2. Right? So now we can substitute the de Broglie wavelength into this expression and try to solve for E, get an idea of the different energy states that are possible for the trapped electron in this case. So if we square this equation, we get L squared equals n squared by 4 times lambda squared, which is h squared divided by 2me. And the different value of the energy states that are possible are n squared h squared divided by 8m squared. So for the ground state energy, we'll put n equal to 1, okay, and we'll call this E1. And the second one, it will be n equal to 2, and so on and so forth. So these are the different energy states that are possible for different electrons. Okay, so basically they gave the prefactor of n squared as alpha, so this will be just alpha n squared. Okay, and so yeah, now in the game we have 4 different electrons that are non-interacting, so we don't consider their electrical potential energies of interaction. So now we have to fill the energy levels using the Pauli exclusion principle. So let's say we have E1, E2, E3, E4 and so on. So how do we fill that? So first we'll fill the electrons in the smallest lowest energy state possible. So according to the Pauli exclusion principle, if you have 4 electrons in the trap, if you take any 2 electrons in the trap, neither of them can have the same value for all the quantum numbers. Okay, so for the one-dimensional trap, the energy of the state depends only on the quantum number n, right? Okay, so let's say if we filled 1 electron in the ground state, and let's say it has a spin of plus half, then the next electron that we are going to be filling must have a spin of negative half, right? Because otherwise they will have the same set of quantum numbers here. Okay, and the third electron will be filled in the second state with some plus half, and the fourth electron will have the negative half spin. So this is how the filling of the electrons is going to look like. If it was a 2-dimensional trap, so there we will write 2 boundary conditions like Lx equals nx lambda by 2 and Ly equals ny lambda by 2. And there, okay, so there we'll have 3 quantum numbers to deal with, nx, ny and the spin. Okay, so here we'll only have 2. Now all we have to do is just add the energy level. So this is the ground state configuration. So we can just add up the energies real quick. If you put n equal to 1, you'll get E1, which is just alpha. So the energies corresponding to these 2 electrons will be 2 alpha. And if you put n equal to 2, you'll get the second energy state's energy, which would be 4 alpha. So add up 4 alpha, you'll get 8 alpha. So 8 plus 2 is 10 alpha. So the ground state energy of the system is 10 alpha. Okay, so A option would be wrong. And in B option, the energy of the highest occupied state is 16 alpha. That is not true, right? The highest occupied state is E2, which has an energy of 4 alpha. So this would be just wrong. And the total energy of the first excited state. Okay, so for the excited state, we just need to see which transition takes the least amount of energy. So of course, it's easier for an electron from the second state to jump to the third state. So if we do that, this will be the first excited state diagram. Okay, so what is the energy in this case? The 2 alpha corresponding to the ground state, right? We have 2 electrons in the ground state. We have 1 electron in the second state, and we have 1 electron in the third state. So this is just 15 alpha, which is 5 alpha above E naught. So C option is also wrong. And in D option, we have the total energy of the second excited state. For the second excited state, we have to check which energy transition takes the least energy. So is it easier to jump from the first state to the second, or is it easier to jump from the second to the third? Okay, so the difference in energy levels between state 1 and state 2 is going to be 3 alpha, right? And between state 2 to state 3, that energy difference is 9 minus 4, 5 alpha. And between these 2 states, it is once again 7 alpha, and it will keep. So the easiest jump to make is from the state 1 to state 2, right? So that is what's going to happen. And of course, there is one empty space in the second state, so this is allowed as well. Okay, so now we can just calculate the energies. Alpha in the first state, 4 alpha plus 4 alpha, which is 8 alpha in the second state, and a 9 alpha in the third state. So this is 18 alpha in total, which is 8 alpha above E naught. So option D will be correct in this situation. So now let's move to the next one. Okay, so now in this problem we have a particle of mass m which is initially at rest at a point x naught y naught. The particle is subjected to a force alpha ti plus beta j. At time t equals 0, alpha is given, beta is given. The angular momentum and the torque acting on the particle with respect to the origin are represented by L and tau. Which of the following are correct? So this is like the multi-correct ones. Okay, so here the position vector at any general time, if it is xi plus yj. Let's just calculate r cross f real quick. So we'll have x multiplied by beta and I cross j will be k cap. And we'll have y alpha t, j cross I is minus k. So we'll have minus y alpha t k cap. So the torque is x beta minus y alpha t in the k cap. So now we can just put 1 by 3 comma half here. Okay, so now we need the time at which the particle reaches 1 by 3 comma half. So that you can just look at the force expression. So this is also the acceleration as well because m is 1, right? If we just look at the y direction, the acceleration is 1 meter per second square. So how much time does it take to cover half meters? So we want half a t squared to be equal to half. So t is just 1 second. So particle reaches this coordinate after 1 second. So what that means is we'll multiply this with 1. So this is 1 by 3 minus 1, which is negative 2 by 3. Option A would be wrong. Okay. In the second case, they're asking us about the angular momentum. So the x acceleration is 2t and the y acceleration is 1. So from here, vx just turns out to be, if you integrate on both sides, t squared. Okay. And vy is just going to be t. So at t equal to 1 seconds, vx is 1, vy is also 1. So the angular momentum will be just r cross mv, which is 1 by 3 comma half crossed with 1 comma 1. So this will be 1 by 3 minus half, which is negative 1 over 6 k cap. Okay, so B option is correct. Now in the third option, we have magnitude of displacement of the particle at t equal to 2 seconds. So the x coordinate from here is going to be t cubed by 3 and the y coordinate is just going to be t squared by 2. So at t equal to 2 seconds, this will be 8 by 3 and this will be 4 by 2, 2. So the magnitude of displacement is 2 times 1 plus 16 over 9 under root. So this is 10 by 3. Okay, so this option is also correct. The velocity of the particle when it reaches the point x comma y, this would be wrong because this is going to be 1 comma 1 rather than 2 comma 1. So the answer, if I didn't make any mistake, is going to be B comma C. Now in this question, we have a conducting square loop of length A, initially located at x equal to 0, is moving with velocity v naught I and in a non-uniform magnetic field of x over x naught. Okay, if all the constants are positive, phi x0 is the magnetic flux passing through the loop when the center is at a point x naught. Okay, so if the center is at the point x naught, okay, so let's say that the situation is somewhere over here where this is x naught and this is where the center is. We have to figure out the flux. Okay, so here let's say the coordinate of the center of the loop at any general time is just x. Okay, here because the magnetic field is varying linearly, right? It has a linear relation. The flux, we can just consider it as the area of the loop a squared times the magnetic field at the center. Okay, and the idea lies in the fact that integral that you have to calculate is basically going to be b multiplied by a dx, right? And the integral of b dx is similar to the calculation of b average, right? Integral b dx over delta x is the average of b in that interval. Now, because b is varying linearly, the average is going to lie at the midpoint. Okay, so if we have an interval of x1 to x2, so this integral will just become b at midpoint, and so that if you multiply it with this delta x, you will get the answer for the integral of b dx. So here in this problem, what we're calculating is integral b a dx. Okay, so we'll take the a outside, and integral of b dx, we have to perform this integral within this interval lying from x minus a to x plus a, x minus a by 2, sorry, to x plus a by 2. So here the interval is a. So integral of b dx will become b at midpoint multiplied by a, which is going to be a square times b at the center of the square. So when x reaches x naught, the magnetic field is b naught. So the flux becomes b naught a squared. So A option is correct. For the EMF, we can just differentiate this, right? So magnitude of EMF is just going to be a square times dB over dt, which is going to be d by dt of b naught x by x naught, which is a square b naught by x naught multiplied by dx over dt, which is the speed of the square loop. So option D would be correct. The EMF is proportional to the speed of the loop. In option C, they're saying the EMF induced in the loop remains the same if the square loop is replaced by a circular loop of radius a by root pi. So even in this case, the flux will be the area of the circle, which is pi r squared times the magnetic field at the midpoint, which is going to be, let's say, BC itself. And here also, if you observe, the area turns out to be a squared, similar to the flux in this case. So option C will also be correct. Okay, so the answer would be ACD according to me. So now in this problem, we have a liquid of density rho that is slowly poured from a beaker into an empty cylindrical glass of cross-sectional area A, resting on a table at a constant volume rate of V. Okay, so it is being poured at a constant volume rate of V. The beaker is at a height capital H from the table, and the water exits the beaker with a negligible speed. Let t equal to 0 be the time at which water initially hits the bottom of the glass, and h be the height of the liquid in the glass at time t. Assuming the water doesn't overflow, which of the following is correct? The total force of the water on the glass when the height h is h by 2 is. Okay, and what they're asking is the force that is exerted on the bottom of the glass. Okay, so it will include the weight of the existing fluid and the impact force of the fluid that comes to rest after mixing with the other fluid, and then we'll also have the force of atmospheric pressure acting at the bottom. So the weight as a function of h is just the volume flow rate is given, it is V multiplied by T. So this is the volume of the fluid that fills the container in T time, and this multiplied by the density of the fluid multiplied by G. So this will be the weight when the fluid level rises to a height of h. Okay, so this is how weight varies with the time, but as we want to write it in terms of the height h, this is just going to be rho A h into G. Okay, so this is the weight of the fluid that is currently present in the container. So now the thing is, there will be an impact force on the fluid body because of the fluid that comes to rest after entering the container. So that impact force is, so let's consider a tiny mass of the fluid delta m, and before entering, let's say it has the speed of v. So now v is just square root of 2g capital H minus small h, right? Why? Because the velocity here was approximately 0 and it fell down a distance of capital H minus small h. So so now after entering, we'll assume that this fluid mass came to rest almost instantaneously. So now if we apply impulse momentum on that delta m mass, F delta t would be the impulse that was applied by the fluid in the container on the delta m mass, and this would be equal to the change in momentum of the delta m mass. So that would be delta m times v. Okay, so the impulse force would be delta m by delta t, which is the rate at which delta m mass enters the container. So this we can write as the density multiplied by the volume flow rate, and I'm just writing the volume flow rate as q for now to not confuse it with v, and this multiplied by the velocity, this multiplied by square root 2g capital H minus small h. So this would be the impulse force that is exerted on the fluid that is present on the container. Okay, and other than this, of course, we'll also have the atmospheric pressure force acting at the bottom. Now the reason why we are not considering the rho g h is because that rho g h was itself because of the weight of the fluid above the container. So we are already including it in this particular term. That's why we are not including it again. So the net force will be just P naught A, which is the atmospheric pressure force, plus rho A G H plus this rho Q, which I'm writing it as V again, times square root of 2G capital H minus small h. Okay, so this will be the force exerted on the bottom of the container. Okay, so now when H equals capital H by 2, I guess this becomes the answer. So yeah, this A option would be correct. And when H tends to capital H, that is basically the height reaches pretty close to the point where the fluid is exiting the beaker. Here, of course, there won't be an impact force because the fluid does not get enough time to gain a speed and stuff. So there won't be any impulse force in this case. So B option is wrong. The total force of water on the glass increases with small h. Okay, so this is a bit complicated. It's not as straightforward because if you observe this term over here, this increases with h linearly, right? So as the height of the fluid increases in the container, this term over here rises linearly, but this term over here, it decreases with an increase in h. So the impulse force that is going down with time and the weight is going up with time. We have to figure out the derivative. It will be rho A G H dot and plus rho V multiplied by 1 by 2 square root of 2G capital H minus small h, okay, multiplied by 2G times negative H dot. So if you take out the rho G H dot outside, what we get is A minus V divided by square root 2G capital H minus small h. Now for some value of small h, this term will become 0. So till that point, the force will increase, and when that point is reached, afterwards the force will start decreasing. So saying that the force on the water will increase with h is wrong. Okay, so and next is the impact force of the water on the glass when small h is h by 4 is. So for that we can just put small h is h by 4 over here. So it will be rho V square root 3G capital H by 2. Okay, option D would also be wrong. So the only correct option over here is option A. Okay, so that's it for this video, guys. I'll bring the other problems later. Yeah, if you have any doubts, you can ask below. And if you enjoyed, do like, share and subscribe. And that's it. Thanks for watching.